After studying this module, you shall be able to understand relation between surface tension and adsorption and derive the Gibbs adsorption equation, know about surface active materials, understand the formation of surface films and surface pressure, and learn about the catalytic activity at the surface. Now we shall study about the adsorption and surface tension and derive the Gibbs adsorption equation. In the last module, we have studied about the phenomena and applications of surface tension. We saw that it is due to the presence of unbalanced forces on the surface of a liquid. The liquid tries to contract its area and attain a minimum value of surface energy. The latter was numerically and dimensionally equal to the force of surface tension. It was observed that the addition of a solute of lower surface tension as compared to that of the liquid results in the accumulation of solute on the liquid surface. This is due to the fact that the solute tends to decrease the surface tension of the liquid and hence its surface energy per unit surface area. J.W. Gibbs derived a quantitative relationship between the extent of adsorption of a solute and the respective change in the surface tension of a liquid due to its addition. This relation is called as the Gibbs adsorption equation and can be derived as follows. For a system consisting of a solvent N1 and a solute N2, that is for a two-component system, the Gibbs energy will be given by equation 1 as G equals to N1 mu1 plus N2 mu2 plus gamma S, where mu1 and mu2 are the respective chemical potentials of the two components, S is the surface area and gamma is the surface energy per unit area. Gamma into S deals with the contribution due to the surface free energy towards the Gibbs free energy of the system. Therefore, the variation in the total Gibbs free energy of the system will be given by equation 2 as dG equals to N1 d mu1 plus mu1 dN1 plus mu2 d mu2 plus mu2 dN2 plus gamma ds plus S d gamma. Since G is a function of temperature, pressure, N1, N2 and S, therefore we have the equation 3 as, or we can write dG in the form of equation 4 as equal to minus S dt plus V dP plus mu1 dN1 plus mu2 dN2 plus gamma ds. Under conditions of constant temperature and pressure, we have dG at constant T and P equals to mu1 dN1 plus mu2 dN2 plus gamma ds as our equation 5. Equating 2 and 5, we get N1 d mu1 plus N2 d mu2 plus S d gamma equals to 0 as our equation 6. In the bulk of the liquid, the analogous expression for the Gibbs free energy change devoid of surface energy will be given by equation 7 as N1 naught d mu1 plus N2 naught d mu2 equals to 0, where N1 naught and N2 naught are the respective amounts of solvent and solute in the bulk phase. As per the thermodynamic condition of chemical equilibrium, the chemical potentials of the components of a system in state of equilibrium must be same in all its phases. On slight perturbation, a new state of equilibrium is achieved and the subsequent changes in the respective chemical potentials of its components in all the phases must also be identical. Therefore, d mu1 and d mu2 in equations 6 and 7 must be same. For equation 7, we have d mu1 equals to minus N2 naught by N1 naught into d mu2 as our equation 8. Substituting the above equation 8 in equation 6, we get N1 into minus N2 naught by N1 naught into d mu2 plus N2 d mu2 plus S d gamma equals to 0 as our equation 9, or N2 minus N1 N2 naught by N1 naught times d mu2 plus S d gamma is equals to 0 as our equation 10, or we can write d gamma by d mu2 equals to N2 minus N1 N2 naught by N1 naught divided by S as our equation 11. Equation 11 involves the difference of two terms on the right hand side, that is the amount of solute that is associated with the liquid at the surface and in the bulk phase. The numerator of this equation thus gives the excessive concentration of the solute present at the surface of the liquid. This, when divided by the surface area, gives the excessive concentration of the solute per unit surface area, abbreviated as gamma 2. Thus, we have gamma 2 equals to minus d gamma by d mu 2 as our equation 12. This equation 12 is termed as the Gibbs adsorption equation. Also, the chemical potential of the solute is given by the expression mu 2 equals to mu 2 star in the liquid phase plus RT ln A2 as equation 13, where mu 2 star in the liquid state is the chemical potential of the pure solute in the liquid phase. Differentiating equation 13, we get d mu 2 equals to RT d ln A2 as equation 14. Using equation 12 and equation 14, we get gamma 2 equals to minus 1 by RT d gamma divided by d ln A2, which can be written as minus A2 by RT d gamma by dA2 as our equation 15. For a dilute solution, we have gamma 2 equals to minus 1 by RT d gamma by d ln C2 by C0, or gamma 2 is equals to minus C2 by RT d gamma by dC2 as our equation 16. This equation is termed as the Gibbs adsorption isotherm. Now, we shall have a look at the surface active and surface inactive materials. The Gibbs adsorption equation 16 derived above is useful in classifying certain substances as surface active and surface inactive materials. If the addition of a substance to a solvent causes a decrease in the surface tension of the latter, the substance is termed as a surface active material. Using the Gibbs adsorption equation, d gamma by dC2 is negative, which makes gamma 2 positive. This implies that the substance has a relatively higher concentration at the surface of the solvent compared to the bulk of the solution. Examples of surface active materials include soaps, detergents, dyes, most organic compounds like fatty acids, alcohols, etc. The limiting value of the decrease in surface tension with concentrations, that is, limit of d gamma to dC2 where C2 tends to 0, is termed as surface activity. On the other hand, if a substance increases the surface tension of the solvent to which it is added, that is d gamma by dC2 is positive, it is called as a surface inactive material. Such materials have a higher concentration in the bulk of the solution as compared to on their surface, that is, gamma 2 is negative. This behavior is termed as negative adsorption, and substances like glycerol, sugars, inorganic salts, etc. belong to this category. These surface inactive materials produce a very small change in the concentration of the solvent and hence increase the surface tension of the latter to a small extent only. The difference in the behavior of these two materials can be explained on the basis of intermolecular attractions operating between the solute and the solvent. If the solvent-solvent interactions are stronger than the ones operating between the solute and the solvent, that is, solute exhibits positive deviations from the Raoult's law, the solute molecules are pushed up from the bulk of the solvent to the surface, thus making gamma 2 positive. This decreases the attractive forces in the surface layer and hence reduces the surface tension of the solvent. On the other hand, if solute-solvent interactions are stronger than the solvent-solvent interactions, that is, solute exhibits negative deviation from the Raoult's law, solute molecules are retained in the bulk of the solution in order to maximize the interactions and gain more stability. Now, we shall have a look at the orientation of the surface active materials. The surface active materials have a specific orientation in the solution, especially when the concentration of the solution is high. Considering the example of a fatty acid in water, the polar groups, that is the hydroxyl or the carboxyl, orient towards the surface of the water and the non-polar hydrocarbon chain points vertically away from the solution. This was mathematically proved by B. Szyszkowski, who gave the relation between the variation in the surface tension of water with the addition of water-soluble fatty acids as given by equation 17 as gamma by gamma star equals to 1 minus x ln C by y, where gamma and gamma star are the surface tension of solution of concentrations C and pure water respectively, and x and y are constants. Rearranging equation 17, we get equation 18. Differentiating equation 18, we get d gamma equals to gamma star into minus x dln c as equation 19, or this can be written as d gamma by dln c equals to minus x gamma star as equation 20. Using the above equation 16 in the equation 20, we get gamma 2 equals to minus 1 by RT into minus x gamma star, which can be written as x gamma star by RT. This is our equation 21. Since the right hand side of the equation 20 is constant, therefore the surface excessive concentration also attains a constant value. It can be thus concluded that the latter does not depend on the hydrocarbon chain length of the fatty acid molecule. This is possible only if the solute, that is the fatty acid molecules, orient themselves in a specific manner with their polar heads attracted towards water and non-polar groups pointing vertically away from it. Now looking at the formation of surface films on liquids. Certain substances like long-chain fatty acids like oleic acid, stearic acid, etc., alcohols, amides, etc. are insoluble in water and have a tendency to spread and form films on the water surface. The orientation of these substances is highly specific, with their polar ends facing towards water and the hydrocarbon chains facing away. Consider a solution of such a substance, say stearic acid dissolved in benzene. When a drop of this dilute solution is added to water contained in a Langmuir tray, after some time the benzene evaporates and the stearic acid forms a thin film on the water surface. The film can be confined between a barrier and a float, against which any force can be measured with the help of a torsion wire. This has been shown in figure. The area of the film can be changed by moving the barrier. If the film is compressed, initially the force required is minimal until a certain critical stage is reached where the force required to compress the film rises steeply. Figure shows the general trend of how the force required to change the area per molecule of the film forming substance varies. Such a curve is called a FA isotherm and is a two-dimensional analog of the three-dimensional PV isotherm. On extrapolating the graph, the value of the critical area comes to be 0.205 nanometers square per molecule. This value of critical area is a reasonable constant for a number of long-chain compounds with polar heads. This indicates that the critical area is independent of the hydrocarbon chain length. At this critical state, the molecules are closely packed, forming a monolayer and oriented in a specific direction as shown in figure 1 on the water surface. This area thus represents the area of cross-section of the molecule. The latter can also be used to calculate the length of the molecule. Figure 2 shows the formation of surface film, that is the Langmuir film experiment, and figure 3 shows a typical FA isotherm. As a result of surface tension on the film-covered surface, a force F acts in the direction shown in figure. If the barrier of the length x moves by a distance dy, then the area of clean water surface increases by amount x into dy, while that of surface film decreases by amount x dy as shown in figure. The net increase in energy will be given by gamma star x dy minus gamma into x dy, where gamma star and gamma are the surface tension of pure water and film-covered surface respectively. The energy is supplied by the movement of the barrier by a distance dy against a force F into x, such that F into x dy equals to gamma star minus gamma into x dy as shown in equation 22. Or we have F equals to gamma star minus gamma as shown in equation 23. It is to be noted that F acts as a surface pressure and is equal to force per unit length of the barrier. It can be seen from figure 3 and equation 23 that the difference between the surface tension of the film-covered surface and clean water surface is very small, unless the film becomes closely packed. The Gibbs adsorption isotherm derived above is given by equation 16 as gamma 2 equals to minus C2 by RT into d gamma by dC2, or d gamma is equals to minus RT times gamma 2 into dC2 by C2 as equation 24. Now, the surface excess concentration is proportional to the bulk concentration, that is, gamma 2 is proportional to C2, or gamma 2 equals to Kc2 as equation 25. Substituting equation 25 and 24, we get d gamma equals to minus RT K Tc2 as equation 26. Integrating equation 26, we get gamma minus gamma star equals to minus RT K C2 as equation 27, or gamma minus gamma star is equals to minus RT gamma 2 as equation 28. Using equation 23 in the above equation 28, we get F equals to RT into gamma 2 as equation 29. The surface excess concentration gamma 2 is also equal to the number of moles N2 sigma of the film forming substance per unit area A. That is, gamma 2 equals to N2 sigma by A as equation 30. Substituting equation 30 in equation 29, we get Fa equals to N2 sigma RT as equation 31, or Fa bar equals to RT as equation 32, where A bar is the area per mole of the substance. Equation 32 is applicable to monolayer formation at the surface and is analogous to the ideal gas law, assuming the gas is two-dimensional in nature. Figure 4 shows the variation in the surface pressure with area of the film-forming molecule. The curves have a very similar appearance to the PV isotherms of a real gas. In fact, the uppermost curves follow the two-dimensional ideal gas law derived above in equation 32. Figure shows the variation in surface pressure with area of the film-forming molecule. The formation of surface films of Langmuir type has diverse applications. The equation 32 can be used to calculate the surface pressure or the area of the molecule. Langmuir and Blodgett gave a very simple method to determine the size of the molecules, results of which match well with those obtained from X-ray diffraction studies. Other applications include measurements like surface diffusion, surface potentials, film viscosity, chemical reactions in monolayers at the surface, reduction in water evaporation using long-chain alcohols, etc. Formation of electrical double layer at the interface and electrokinetic effects. Whenever two phases of dissimilar chemical composition are in contact with each other, an electric potential difference gets developed, resulting in charge separation across the surface. If one such phase is a metal electrode, say positively charged, present in the region X less than equal to 0, and other is in the electrolytic solution bearing corresponding negative charge and present in the region X greater than equals to 0, different charge distributions are possible corresponding to different potential fields. This has been depicted in figure. The different charge distributions possible are as follows. A. Helmholtz double layer. The negative charge of the electrolyte solution corresponding to the positive charge of metal electrode is present in a plane at a short distance delta from the metal surface. This type of double layer containing charges at a fixed distance is called Helmholtz double layer, shown in figure B. Goy-Chapman double layer. This layer contains the corresponding negative charge not at a fixed distance but in a diffused manner throughout the solution. The situation can be considered analogous to a diffused atmosphere surrounding an ion in the solution as shown in figure C. Stern double layer. This type of double layer is a combination of fixed and diffused double layers. A fixed layer containing small negative charge is present at a distance delta, and the remaining negative charge required to balance the positive charge of the metal electrode is present in the diffuse layer lying beyond this distance. Another possibility is that the fixed layer contains more than the required negative charge and the diffuse layer is positively charged as shown in figure. The possibility of specific ions, cations or anions getting adsorbed on the metal surface is also included in this theory. We can also have the other possibility of the metal electrode being negatively charged and the electrolyte solution bearing the corresponding positive charge. Figure shows various types of double layers. Y-axis displays the potential relative to that in the solution. Another successful model given by Graham distinguishes between the two planes of ions. It proposes the existence of inner Helmholtz plane at a distance of closest approach of the centers of the chemisorped anions to the metal surface. Beyond this plane, at a distance of closest approach of the centers of hydrated ions, lies the outer Helmholtz plane. The diffuse layer begins at the outer Helmholtz plane as shown in figure. This model satisfactorily explains the effects related to double layer. Figure shows the electrical double layer showing inner and outer Helmholtz plane. The phenomena of double layer formation leads to charge separation at the solid-liquid interface. Due to this, the particles in a heterogeneous fluid, that is, fluid containing particles, get affected in the presence of an electric field, producing electrokinetic effects. Some of them have been discussed. A. Electrophoresis. It is defined as the movement of charged particles suspended in a liquid under the influence of an electric field. These suspended particles carry charge, which is the sum of the charge present on the particle and the charge present in the fixed portion of the double layer. On the other hand, the mobile diffused part of the double layer, being oppositely charged, moves in the other direction. B. Electroosmosis. It is defined as the movement of the liquid through an immobilized set of particles, porous membrane or plug, in response to an applied electric field. It occurs due to the force exerted by the field on the oppositely charged liquid present inside the charged porous membrane or disc. When these ions move, they drag along the liquid, which solvates them. The latter moves with a uniform velocity called electroosmotic velocity. This can be explained by taking a device filled with water and fitted with a fixed porous quartz plug as shown in figure. The diffuse and hence the mobile part of the double layer is positively charged. When the electric potential is applied, the positive charge moves to the cathode compartment, dragging along water with itself. Figure shows the process of electroosmosis. C. Electroosmotic counterpressure. If we wish to stop the above process of electroosmosis, some pressure difference will have to be applied across the system. The latter is termed as electroosmotic counterpressure. D. Streaming potential. If we force water to flow through a porous plug, it carries charge from one side to the other. This flow of countercharges inside the plug causes the charges to accumulate, creating a potential difference called streaming potential between the electrodes. E. Streaming current. When the two electrodes are short-circuited, the current that flows through the plug is called the streaming potential. F. Sedimentation potential, or the Dawn effect. If we consider a suspension of particles, the particles upon settling down under the effect of gravity carry their respective charges towards the base of the container. The charge on the diffuse part of the layer, on the other hand, remains in the upper part of the vessel. This creates a potential difference between the upper and the lower part of the container, known as sedimentation potential. If sedimentation is produced by the centrifugal force, the process is called as centrifugation potential. The electrokinetic effects discussed above come into play due to the reason that the entire double layer is not fixed. Instead, some part of it is loosely bound to the solid surface and hence is mobile in nature. Their magnitude depends on the amount of charges present in the mobile part of the double layer. The latter in turn depends on the potential developed at the dividing line or the shear surface between the fixed and the mobile part of the double layer. This potential is called as zeta potential. Thus, it can be concluded that the magnitude of all electrokinetic effects depend on the magnitude of zeta potential. Now, we shall have a look at the catalytic activity at the surface. A catalyst is a substance that affects the rate of a chemical reaction without itself getting used up for the same. It does not undergo any change in its mass or its composition. It only helps in the faster attainment of the reaction equilibrium. It does so by changing the activation energy pathway leading to the reaction. In general, the process of catalysis can be classified as homogeneous catalysis. When the catalyst is present in the same physical state as that of the reactants, it is termed as homogeneous catalysis. For example, sulfur dioxide plus oxygen in the presence of nitric oxide gives sulfur trioxide. B. Heterogeneous catalysis. When the catalyst is present in a different phase as that of the reactants, the process is called heterogeneous catalysis. For example, we have the Born-Haber's process occurring in the presence of finely divided nickel to give ammonia. C. Autocatalysis. When one of the reaction products acts as a catalyst for the reaction itself, the process is called autocatalysis. For example, the decomposition of KMnO4 gives MnO2, which catalyzes its decomposition further. Comparing homogeneous and heterogeneous catalysts, the former are often selective towards the formation of a desired product and operate at low temperature and pressure conditions. They, however, are difficult to separate from the reaction mixture. On the other hand, the heterogeneous catalysts are often robust in nature and offer a major advantage of being capable of easy removal from the reaction mixture. In industries, most of the chemical reactions make use of solid catalyst. For example, the Born-Haber's process involves the synthesis of ammonia from hydrogen and nitrogen gases in the presence of finely divided iron as a catalyst. Contact process for the synthesis of sulfuric acid involves the oxidation of sulfur dioxide to sulfur trioxide in the presence of platinized asbestos or vanadium pentoxide. Polymerization of alkenes using phosphoric acid distributed on diatomaceous earth, etc. The most common examples of heterogeneous catalysts used are the transition metals associated with partially vacant d orbitals like chromium, tungsten, manganese, iron, cobalt, nickel, palladium, platinum, copper, silver and gold, metal oxides, Al2O3, Cr2O3, Vu2O5, ZnO, NiO, Fe2O3, or acids like H2SO4 and H3PO4. There are a number of commercially important reactions that make use of solid catalysts. For latter to be effective, a very important requirement is that one or more reactants should be chemisorbed on their solid surface. These catalysts are known to substantially decrease the activation energy required for the reaction. For example, consider the decomposition of hydrogen iodide to give hydrogen gas and iodine. This reaction involves the activation energy of about 44 kilocalories per mole. The latter decreases to a value of 25 kilocalories per mole and 14 kilocalories per mole in the presence of gold and platinum as catalysts respectively. Some of the important features of solid catalysts are: number 1, activity. The activity of a catalyst depends on the strength of the chemisorption of reactants on the solid catalyst surface. In other words, it depends on the value of enthalpy of adsorption. If the latter is low, it would mean the extent of adsorption is low, leading to a slow reaction. On the other hand, if it's large, the reactants will be held very tightly to their absorption sites, thereby becoming immobile. This inhibits their tendency to react with one another and/or leaves no space for others to get adsorbed, again leading to a slow or no reaction at all. Hence, a good catalyst must have moderate values for the enthalpy of adsorption of reactants on the solid catalyst surface. Number 2 is the selectivity. A good catalyst should be highly selective in nature so as to give the desired product in a given reaction. Shape-selective reactions involves those reactions that depend on the size of the reactant molecules and catalyst pore structure. For example, the use of zeolites for cracking hydrocarbons. Number 3 is the surface area. A good catalyst must have large surface area for the reactants to get adsorbed onto it. To increase the exposed surface area, the catalyst is finely divided or commonly distributed on the surface of a porous carrier like alumina, Al2O3, silica gel, SiO2, charcoal, etc. These carriers may be inert or may contribute to the catalytic activity. There are certain substances that increase the activity of a catalyst and its lifetime. They are called as promoters. For example, iron used in the Born-Haber process contains small amount of Al2O3 that prevents the sintering process, that is the joining together of small iron crystals. Formation of large crystals decreases the surface area and hence the catalytic activity. Contrary to promoters, there are certain substances termed as poisons which decrease the catalytic activity by binding strongly to the catalyst. These may be present as impurities in the reactants or may be formed as one of the byproducts in the reaction. Examples of such substances generally include compounds containing species with lone pair of electrons like H2S, carbon monoxide, carbon disulfide, or heavy metals like lead, mercury, etc. A very important example in the reaction occurring in the catalytic converters of the automobiles. This involves the use of finely dividing platinum to convert carbon monoxide from the exhaust gases to carbon dioxide. Lead-free gasoline must be supplied to the cars equipped with catalytic converters, as lead acts as a catalytic poison, decreasing the efficiency of the latter. The general mechanism for the fluid phase reactions catalyzed by solid heterogeneous catalysts involve the following steps. Number A. Diffusion of the reactant molecules onto the solid surface of the catalyst. B. Chemisorption of at least one of the reactant molecules on the solid surface. C. Chemical reaction between the adsorbed molecules present on the adjacent sides of the solid catalyst surface, or a chemical reaction between an adsorbed molecule and fluid phase molecules colliding with the surface. D. Desorption of the products from the catalyst surface. E. Diffusion of reaction products away from the solid catalyst surface onto the bulk fluid. If the reaction involves two reactant molecules that are adsorbed on the solid catalyst surface, migration of the adsorbed molecules on the surface may occur between steps B and C. The overall reaction mechanism is often complicated, and it is more likely that one of the above steps is slower as compared to the other. In this case, the rate of this slowest step is considered. Let us consider only the solid catalyzed reactions of gases, where step C is the slowest. When two chemisorped species are reacting on the solid catalyst surface in this step, the reaction is said to occur by a Langmuir-Hinshelwood mechanism. On the other hand, if in this step a chemisorped species reacts with a fluid phase species, the mechanism is called Riddle-Eley mechanism. The former are said to be more common than the latter. Now, discussing the Langmuir-Hinshelwood mechanism, we have, for the sake of simplicity, let us consider the step C consists of a single slow unimolecular or a bimolecular elementary reaction followed by one or more steps. The rate of adsorption and desorption is higher than the rate of chemical reaction of all species. Therefore, the state of equilibrium between adsorption and desorption is maintained for all species in a reaction. Under these conditions and the assumption that the surface of solid catalyst is uniform, which actually is not true, we can use the Langmuir isotherm. The conversion rate of a heterogeneous catalyst per unit surface area is given by Rs equals to J by S equals to 1 by A into 1 by nu B into dNB by dt as equation 33, where J is the conversion rate, S is the catalytic surface area, Nb is the stoichiometric number of any species B in the reaction. If the elementary reaction on the catalyst surface is unimolecular in nature, that is A gives rise to C plus D. The conversion rate of a heterogeneous catalyst per unit surface area Rs is proportional to the number of adsorbed A molecules per unit surface area, that is Na by S, which in turn is proportional to the fraction of sites covered by A molecules as theta A. Therefore, we can write equation 34 as Rs equals to K into theta A, where K is the rate constant. If the products C and D also compete with the adsorption sites on the solid catalyst surface, we use a form of the Langmuir adsorption equation where more than one gas is adsorbed on the adsorbent surface, that is theta A equals to KAPA divided by 1 plus KAPA plus KCPC plus KD into PD. The rate law is then given by Rs equals to K theta A, or we can have equation 35. If the products are weakly adsorbed on the solid surface, that is Kc Pc plus Kd into Pd is much smaller than 1 plus Kapa, then the rate law becomes Rs equals to K times Kapa divided by 1 plus Kapa as equation 36. Using above equation 36, we get Rs equals to K into Ka into Pa at low pressures and Rs equals to K at high pressures as equation 37. Thus, we find that the reaction becomes of the first order at low pressure and of the zero order at high pressure. The latter can be explained by the fact that at high pressure, the surface gets completely covered by a monolayer of gas molecules, showing no further increase in the rate with increase in the pressure. Example is the decomposition of phosphine pH3 gas in the presence of tungsten as the catalyst at 700 degrees Celsius. In the reaction follows first order kinetics below 10 to the power minus 2 torr and zero order above 1 torr. If the elementary reaction on the catalyst surface is bimolecular in nature, that is A plus B gives C plus D, and both the reactants are adsorbed on the catalyst surface, then the rate law is given by equation 38 as Rs equals to K into theta A into theta B. Again, using the Langmuir adsorption equation for non-dissociative adsorbed species, we get Rs as given by equation 39. If the reactant B is strongly adsorbed as compared to other species, then we have Kb into Pb is much greater than 1 plus Ka Pa plus Kc Pc plus Kd into Pd. Then Rs is given by equation 40 as K times Kapa by Kb Pb. In this case, the reactant B inhibits the reaction as it is more strongly adsorbed than the reactant A. The fraction of surface covered by molecules of A goes to 0. Therefore, the rate of the reaction Rs equals to K theta A into theta B goes to 0. The rate of the reaction will be maximum when the two reactants are adsorbed at equal rates. In case of Riddle-Eley mechanism, let us consider the following bimolecular reaction. A adsorbed plus B gaseous gives products. Since one of the reactants is in the gaseous phase, the rate of collision of B with the catalyst surface will be proportional to its partial pressure Pb. Thus, the rate is Rs is proportional to theta A into Pb, or Rs is given by equation 41 as equals to K times theta A into Pb. The value of theta A can be substituted to get the desired rate law. In the cases where the reaction molecules undergo dissociation, appropriate value of theta A discussed in earlier modules will have to be substituted to get the rate law. Now we shall summarize what we have learned in this module. J.W. Gibbs derived a quantitative relationship between the extent of adsorption of a solute and the respective change in the surface tension of a liquid due to its addition. The Gibbs adsorption isotherm is given by gamma 2 equals to minus C2 by RT into d gamma by dC2. Based on this equation, certain substances can be classified as surface active and surface inactive materials. The surface active materials have a specific orientation in water, that is, polar heads face towards the water and nonpolar groups point vertically away from it. The two-dimensional ideal gas law applicable to surface film monolayer formation at the surface is given by Fa bar equals to RT. Whenever two phases of dissimilar chemical composition are in contact with each other, an electric potential difference gets developed, resulting in the formation of double layer across the interface. The formation of a double layer formation at the solid-liquid interface produces several electrokinetic effects. Many commercially important reactions make use of solid catalysts. For catalysts to be effective, an important requirement is that one or more reactants should be chemisorbed on their solid surface. For heterogeneous catalysis, Langmuir-Hinshelwood mechanism is commonly followed as compared to Riedel-Illet mechanism.